Hey students, how are you? Let's continue class 14 on the course Linear Algebra and Differential Equation. And today we'll see some simple population models and first order differential equation. So just last time we have seen the Malthusian growth, and this Malthusian growth is modeled by this differential equation, which is the simplest mathematical model of population growth. Which is obtained by assuming that the rate of increase of population here, rate, as I told you last time, it is a certain derivative with respect to time. The rate of increase of the population at any time is proportional to the size of the population. So we have already seen last time, yeah, it was like the population of bacteria, if you remember, and we have said that the rate of this dp by dt is proportional with p. That's why we have modeled this way, and just like remember where k is positive constant, and just like separating the variable and integrating, and just it is like this, yeah, because it is easy. You can integrate, yeah, you can write dp by over p and k dt, and this is separable and it's already separated, and upon integrating this will be ln of absolute value of p, and this will be kt plus c. So p is like what? P at t is like e is the power of c plus kt, which means we can say that it is some constant p naught times e is the power of kt, where p naught is equal to e is the power of c to many. So where p naught denotes the population at time t naught, which means it's easy that you obtain the constancy. This law predicts an exponential increase of the population with time, yeah, because this one is exponential, as you can see it. When t increases, the population also increases to mean. So this law predicts an exponential increase in the population with time, which gives reasonably accurate description of the growth. Yeah, this is simple model, but like you may be encountered to find such questions like it is called the Malthusian growth model, as I told you, and it takes the time taken for such a culture to double in size is called the doubling time. So you may be asked to find the doubling time. The doubling time is like the time in which the population doubles in size. And this is like you can denote by TD. T is time and D is for the double. And like the population at TD, that is double time, is simply 2 times of P naught. Therefore, if we substitute in the formula, because we have already P naught T, this is P naught T formula. The P naught T formula is what? P naught at T is simply, it was P naught is a power of kt, yeah. Now when t is like td, this p naught at t will be what? 2 times of p naught. Doubles, yeah, this is what double mean. Therefore, upon substituting here, it will be what? 2 times of p naught equal to p naught e the power of kt. Therefore, you can cancel p naught by p naught, and e raised kt is the same as 2. This t is like t double. Therefore, we can say that ktd is the same as ln of 2, and td is simply equal with ln 2 over k to me. This is like the doubling time. Td is like 1 over k times ln of 2 to me. This is how to find the doubling time. That is the time in which the size of the population doubles. Here we go. We have a good example. It says the number of bacteria in a certain culture grows at a rate that is proportional to the number present. If the number increased from 500 to 2000 in 2 hours, Determine the number present after 12 hours. This one, the first, and the second is the doubling time. The doubling time. So this is easy questions, yeah? Let's see one by one. So the behavior of the system is governed by the differential equation, that is a Maltesian. dp by dt is simply equal to kp, and we have seen that this is the general solution. Now it says if the number increased from 500 to 2000 in 2 hours, because it is like bacterial population, it is increasing exponentially, we have said it. Therefore this is at 0. Maybe you can say that p at t is equal to 0 is 500, and p at t is equal to 2 is 2000, because in 2 hours it says. So the time is in hours, therefore at t is equal to 0 as time t when the population is 500, just this is to mean. Therefore p of t will be what? P of t will be at 0. At 0 this will be 500, so we can say that pt is 500 times e to the power of kt. What remains is we have to find k, yeah? We have two constants, p naught and k. Therefore, we have to substitute p naught, which is 500. And what about k? We have to find k. How to find k? We can use the second auxiliary, this one. P at t is equal to 2 hour is what? 2000. Therefore, we can obtain the value of k to mean, like this. It's easy. You see, p at 2 is 2000. This implies that 2000 equal to 500 times e to the power of k. Then upon applying a logarithm in both sides, we can obtain k is what? 1 over 4, or ln of 4 over 2, which is equal with ln 2. We can see that. Therefore, once we obtain this k, just we can substitute in the general equation pt. This is the value of p naught, and e to the power of t, this one is the value of k to mean. Now we have like the general solution, and it will be easy like to find the number of bacteria just like after 12 hours. Now instead of t, we will simply substitute 12. That's all. 500 is the power of 12. This is time. Then ln 2, it will be around 2,048,000 to mean. This is the number of bacteria after 12 hours. So the main thing is like you should construct the solution, okay, of the population bacteria. Then once you develop the population, which will be only dependent in t, then just like you can find the number of the bacteria after certain hours by substituting the hour in the place of time to mean. Secondly, the doubling time of the system is just like we have proved that the doubling time is 1 over k ln 2, and we have that this is 1 over, this is ln 2. What about k? K is ln 2, and we have already found here ln 2. Therefore, just upon simplifying, it will be 1 hour. Which means like after 1 hour, the population of the bacteria will be what? 1000, because this is p at t is equal to 1 hour, and p at t is equal to 0 is like 500. So when td is like 1 hour, like after 1 hour, the population of bacteria doubles. This is easy question. But like this Maltesian growth might not be realistic. Okay, might not be realistic. Therefore, like we need to find more realistic model, like the logistic population model. This logistic population model is more realistic than that of the Maltesian. In why, we may say why, just we can discuss. It says the Maltesian growth that we have discussed doesn't provide an accurate model for the growth of the population over a long period of time. That's true. To obtain a more realistic model, we need to take account of the fact that as the population increases, several factors will begin to have an effect on the growth rate. Yeah, for example, there will be increased competition for the limited resources that are available. Yeah, and increase in disease. It will also overcrowding of the limited available space. So this all of which could serve like to slow what? The growth rate. You see, it slows the growth rate. Therefore, the model that we have to develop shouldn't be the Maltesian growth, that which is the growth, I mean the Maltesian growth doesn't uh, include or doesn't assume such factors, okay? So for this reason, the rate of change of the population where this rate of population could be factored by uh, factors like what I have told you, like that hinders the growth rate, must be modeled this way. That is, dp by dt must be equal with bt minus dt times of p, where bt is simply what? The birth rate, okay? The birth rate. And this is what? Days rate. dt means like the days rate. Why we are subtracting the days rate from the birth rate? Because of these factors. We have different factors that will begin like to hinder the growth rate. Yeah. So like the factors could be increasing competition for the limited resources that we have. Maybe it could be due to disease. Maybe it could be due to overcrowding of the limited available. So just like there has to be some deduction, yeah, from the birth rate. Therefore, this is more realistic model. That is the logistic population model than that of the Maltesian growth. Okay. In the more general, it says, let me use a marker. In the more general situation of interest now, the increased competition as the population grows would result in a corresponding increase in the death rate per individual. This is also right. Therefore, we have to consider a certain assumptions here also. So perhaps the simplest way to take account of this to assume that the death rate per individual is directly proportional to the instantaneous population, and that the birth rate per individual remains constant. So now the logistic model must be modeled this way. It was like dp by dt, birth rate minus death rate times p. But now we are saying that the increased competition as the population grows would result in a corresponding increase in the death rate. That shows like the direct relationship, which means the death rate per individual is directly proportional to the instantaneous population. That's why we are using this one. Okay, p naught minus d naught p times p, and this is like the initial condition. Okay, initial condition. Okay, so like this b naught and d naught are simply constants, and it is useful to write the differential. This differential equation could be equivalently written this way: dp by dt equal to is r times 1 minus p over c times p, where like r is b naught, which is like direct, and of course c could be p naught over d naught to mean. And this equation, this equation is simply called the logistic equation, and the model is called the logistic model to me. So this is important because we are in the logistic model that we have, and where am I? I'm lost. Yeah, I'm here. Yes. So this model is called the logistic equation. And maybe you wonder what C mean, yeah? That is the carrying capacity or the limiting population that we have explained last time. C is the carrying capacity, okay? Or the limiting population that we have discussed last time to me. And of course, you can see that this is separable differential equation. Yeah, we have dp here. So if we take 1 minus p over c times p down here and multiply dt with r, just it will be easy to integrate. Therefore, it is easy to find the general solution for the logistic model here because it is separable differential equation. You see here how to find the analytic solution to this differential equation. Just like if you integrate both sides for this model dp by dt, just it will be c over p, c minus p dp, and this will be rt plus 1, yeah? Because it was r dt, so upon integrating, it will be rt plus c1, some constant. And just like remember some techniques of integration. So this integration seems difficult, but not actually difficult to integrate because you can use the partial fraction method. So upon using the partial fraction method, you can write c over p times c minus p can be written equivalently like this 1 over p plus 1 over c minus p dp. Then it will be easy to integrate, yeah? Because the integration of 1 over p dp is ln of p, and the integration of 1 over c minus p is like minus of ln of c minus p. Therefore, it will be combining this. This will be ln of the integration of, ln of the absolute value of p over c minus p is equal with rt plus c1. Therefore, what is p over c minus p? It will be what? Either e raise rt plus c1 to me. And of course, we can write this as e raise c1 times e raise rt, and we can consider this e raise c1 as a certain constant. Maybe we can call it c2 like this. That's why it is written this way, p over c minus p. And of course, just you can rearrange this algebraically, then you can solve for p explicitly, yeah? And this is the explicit solution for p. So p of t will be like c2 times c e raise rt over 1 plus c2 e raise rt to mean. And this pt and this are the same, yeah? This and this are the same one and the same equivalently. Therefore, if we substitute the initial condition p at 0, which is p naught, we can find directly c2, yeah? We can find c2. Just like you can see it here. If t is 0, this will be 1, yeah? This will be 1. So this will be c2c. This will be over 1. So this will be p naught p. Therefore, this will be right, p naught over c minus p. And upon inserting in place of c2 here or here and here, this will obtain directly the solution for the logistic model is like pt equal to c times p naught over p naught plus c minus p naught is the power of minus rt. So this is good. And of course, yeah, this one is the same. This is a solution. And here, just like we make two comments on this solution 1.53. First, it says, we see that due to the negative exponent of the exponential term in the denominator here, to mean the negative exponent in the denominator, as t goes to infinity, what do you expect? As t goes to infinity, this expression goes what? This expression goes what? As t goes to infinity, we know that is the power of minus rt goes what? To 0, yeah? Therefore, if this one is 0, which means this will be directly 0, therefore you'll obtain p at t will be what? Here I can write p at t will be what? cp naught over p naught, which means you'll obtain c, yeah? Which is the carrying capacity or the limiting population volume. You see, when t goes to infinity, just like p of the population at the population will be approaching to the limiting capacity or the carrying capacity. The carrying capacity. This is one remark that you should know. Yeah, this is independently of the initial population here. And secondly, this equation could be equivalently written this way. Like if you divide this by c all over c, you see, over c over c. So this will be like this, p naught t. will be the same as P naught over C plus 1 minus P naught over C times E raised minus RT. Yeah? Then it says it follows that if P naught is very small, look, P naught is very small compared to the carrying capacity C. This will be what? This will be 0, yeah? This part will be 0. This part will also be 0, yeah? This goes 0, this goes 0. Therefore, this will be what? P naught over 1. No, yeah, 1 times e the power of minus RT. Therefore, this will be P naught e the power of RT, yeah? It will be like this, which means if P naught is very small, just like we can approximate P RT, it will be the same as P naught times E raised RT like this. But we have said that this is the Maltesian, yeah, the Maltesian population, So like it is possible to obtain the Maltesian population just like as an approximation for the logistic model, provides that if our P naught is what? Very small intervals or small time interval. This is what we can say it. So these are like two important things that you should know. As t goes to infinity, just in P as t will approach to the carrying capacity. And the second is the Maltesian population model, this one to me, does approximate the logistic model for small time interval to me, for small time interval. These are the two remarks that you should know. Okay, we have here as an additional example, it says the initial population, which is measured in 1,000 of a city is 20, which means 20,000. Then after 10 years, this has increased to 50.87 thousand. And after 15 years, the population is 78.68. Now the question is, use the logistic model to predict the population after 30 years. So we have this, yes? P at 0 is 20,000. P at 10 years is what? 58. P at 15,000 is what? 78.68. Now we are asked to predict the population after 30 years. So these conditions are what? The auxiliary. Yeah? These are the auxiliary conditions. This one, and this one. And like we are asked to use what? The logistic model. Yeah? The logistic model is this one. Yeah? This is P naught to me. Because the logistic model says P at T is P naught C over P naught plus C minus P naught E raised minus RT. That's what we have shown, yeah, here. This is the logistic model. Sorry. Therefore, just like we use P naught upon substituting, we obtain this one. Now we have to impose the second auxiliary at 10, which is 50.87, and at 15, which is 78.68. Then these both things will help us to find what? The constant C, the carrying capacity, as well as R. Yeah. So you see, like we have this equation, just like this. So just actually, this might not be easy to use your hand, or maybe you can use calculator actually. Otherwise, you can use softwares like Maple, and like solving these two systems. I mean, these two equations, just you will obtain the values of C and R, which is R is 0.1 approximated, and C, the limiting capacity is 500.37. That is approximation. You can see. Now we can substitute in the logistic model, and upon substituting in the logistic model, P at T will be given as this one, which is, you can see that it is only dependent on time T. Now, just like the population after 30 years is simply substituting 30 here, yeah, in place of T. Then P at 30, which is like the population after 30 years, will be what? 227.87 thousand, yeah, because we have said it is 1,000 to mean. So it is easy, see? And graphically, we can obtain here, just like this is the solution curve corresponding to the population model that we have discussed. And the population was, of course, measured in thousands. These are in thousands, yeah? Yeah, these are in thousands, thousands. And you see, we have said that if it is a good model, we have what? Maximum value, it must touch what? The carrying capacity, yeah? The carrying capacity is 500. That's why we are having here. You can see it here. This is a carrying capacity. Yeah. Also, you can obtain from here the carrying capacity. Yeah? Sorry. You can also find the carrying capacity from the logistic model here. Yeah. If you apply the limit of PT as t goes to infinity, you see, you will obtain approximately 500 to me. You can check it here because this will be what? This will be 0. Then 10,000 divided by 20 is around 500 to me. That's true. So this figure is showing how the model is nice because of the carrying capacity to mean. The second part of today's topic is about the differential equation, which is the linear differential equation. And we have that the differential equations that can be written of this form: ax, mind you here, this is function of x, dy by dx plus p of x times y, which is equal to a certain function r of x, which this ax, bx, and r of x are functions defined on a certain interval ab, is simply called the first order linear differential equation. So we should assume that this ax must be different from 0. Yeah, this must be different from 0. If it is 0, of course, this will not be what? Completely not differential equation. So because we are talking about the differential equation, this ax must be different from 0. If it is different from 0, which means we have right to divide by non-zero, and non-zero like this, we can divide it, yeah? So upon dividing, we will obtain this dy by dx plus p of xy, q of x, where this p of x could be what? P of x must be what? P of x over a of x. We can see it here. And this q of x could be the same as what? R of x over a of x. Therefore, just this idea behind the solution technique for this differential equation could be written to the differential equation, which is in a more formal way or in a more comfortable way, this way to me. And once we are able to write the differential equation this way, it will be easy to find the general solution, because if d by dx of a certain function is f of x, which means it is ready to integrate. Yeah? It is easy to find the general solution to the differential equation. Just it will be a matter of integration to me. Okay, let me show you practically solve the differential equation, this one. So is it linear or first order linear differential equation? That's the point. Maybe yes, you can say it. Yeah, that is yes. If you want, you can multiply by x, just like by this one, 1 over x. So if you multiply by x, this will be x dy by dx plus y, which is equal to x e raised x. Yeah. Therefore, this is, of course, first order linear differential equation. Now, just like if you remember the product rule of differentiation, what is d by dx of xy? You remember d by dx of xy. You can say that this is y plus, because the derivative of x is 1 times y is y, plus x times the derivative of y, which is dy by dx. Can you see it here? So this differential equation is equal with this one, and this is the same as d of xy to me. I can say this is d of xy. So if d of xy is x times e raised x, just like if we integrate, it will be what? D by dx. Yes, it will be easy to integrate, yeah? Therefore, we have that this d by dx of xy is equal to, just like x times e raised x. Therefore, if we integrate both sides, this will be what? X by x. This will be like this, integrating. Yeah, then in order to integrate this, you can use what? Integration by parts. Yeah, so upon using integration by part as your integration technique, you'll obtain x e raised x minus x plus c. Then if you can solve for y, and y at x will be like 1 over x times this function. So this is like the general solution for the differential equation to me. So the question is like, just we have to generalize how to find the first order differential equation. So in this case, like we were multiplying by x, yeah? When we multiply this thing by x, just like the things are changed into more simple way. Therefore, similar to this, we have to find a general formula that changed the first order differential equation into simpler and integrable form of this way, like this, as an appropriate function like this. So in this case, we have to find the term called the integrating factor. If we find the integrating factor, yes, it will be easy to solve first order linear differential equation to me. So just like consider the example what we have said, and it was of this type. We now consider possibility of multiplying the general linear differential equation this way: dy by dx plus p of xy equal to g of x. Consider this is like the first order linear differential equation that we have. And if we are going to multiply by non-zero function, say it I of x, just like we have to multiply 3 of this both side, just like chosen in such a way that the left-hand side of the resulting differential equation will be of this type: d by dx of I of xy. Remember, in the first example, we have what? D by dx of xy, like this, xy. Just in similar way, we have to write d by dx of ix times y. So by the product rule, what is d by dx of ix of y? Just like it is simple like this, yeah? Because this will be I times dy by dx. Just this is multiplying by I. Okay, the identity, we have I, here also I, here also I. Now, just like we have to use the product rule for d by dx of ixy is the same as what? I times dy by dx plus what? d by di by dx times y, yeah? Times y. That's why we have here. This is right, as I have said it here. Now, here, this and these are the same. Therefore, let's compare 1.65 and 1.66. This is 1.66 and this is 1.65. And these are one and the same. Therefore, we can equate to each other, because d by dx of iy is the same as I times of qx. You can check it, provide that the function I of x is the solution to this one to me. But if you equate both of them, you can see that this and this are the same, yeah? This and these are the same. So we can cancel just like this. And here we have p of x iy, and this one is di dxy. So we can have just like to cancel this function y by y. Therefore, we remain with what? Dy by dx, you can see it here, is the same as p x I, like this. Now, you see, this is separable differential equation. That is easier. It is separable now. If this is separable differential equation, I can write like this: yes, di over I, which is equal with what? P of x dx, yeah? Now, integrating both sides, this will be what? Ln of absolute value of I. And this will be what? The integration of P of x dx. Of course, you can say plus C. See it here, the same. So there is one step here to me, okay? Before obtaining this, you have to go through this. Therefore, what is I of x? It will be e raised the integration of what? P of x dx. Because e the power of c is another constant, maybe you can write was c1 times e the power of the integration of p of x dx. And it says where c1 is an arbitrary constant, therefore we can use c1 equal to 1. Therefore, our I of x can be written as this one. E the power of the integration of p of x dx. And this is called the integrating factor. Okay? This is I represents for the integrating factor, I of x. So I of x is always what? E the power of the integration of p of x dx. Where p is this one, okay? dy dx plus p of xy, which is equal to q of x. You have to write first in this standard form. Otherwise, it will be hard to find the integrating factor. Therefore, this is this one. So this is our integrating factor, and it says like multiplying the linear differential equation this way by the integrating factor reduces it to the integrable form of this one, okay? D by dx of this is the integrating factor I, okay? This is I times y, which is equal to q of x times the integrating factor. This is I. This is q. This is I. This is y, to mean in short. Therefore, upon integrating this, you'll obtain y at x, y of x is e the power of, which is e the power of the negative of p of x, d of x, times the integration of q of x times the integrating factor dx plus. This is a general solution, okay? But you don't need like to memorize this general solution. It's not a must to memorize. For example, sometimes I forgot to memorize this formula, but I know how to drive. For this reason, this is not like mandatory to know. Therefore, you see, knowing this integrating factor, it will be easy to find like the general solution. And we have remarks. The integrating factor, this is called integrating factor for the differential equation. And since it enables us to reduce the differential equation to the form that is directly integrable. That's the advantage, okay? It will help us to reduce the differential equation to the form that is directly integrable, okay? And the second, it is not necessary to memorize the long formula, this one that I told you here. And not necessary to memorize the formula. In a specific problem, we first evaluate the integrating factor, and we can use directly the general first order differential equation, which is this one. You can use 1.69. Okay, let's support by example, and hope you will understand it fully. See the example here. Yes, the question is to solve this differential equation first order, as well as with initial condition. See, dy by dx, xy. So this one is what? Where is your p of x? Your p of x is what? X to mean. Because dy by dx, the standard is what? Dy by dx plus p of xy. You remember here? Yeah, this one. And equal to what? Q of x. You have to come up. So this one is, the rest is q of x to me. So this one is your q of x. X times e raised x squared over 2, which is q of x, a function of x as you see. X times y, yes, p of x is what? X, and y is y, and dy by dx as it is. Therefore, we have said that our integrating factor is simply what? We have said that our integrating factor is e the power of the integration of p of x d of x. But in this case, our p of x is what? X dx. That's why we are here. And of course, the integration is easy. Integration of x is x squared over 2. So I of x is what? This one. And we have reduced this differential equation into d by dx. We have said that d by dx of what? I times y. Yeah? I times y, this one, in short. Here it is, I times y is the same as q times I. I told you. Q times I. Yeah? What is q? Q is here, which is e to the power of x squared over 2 times I. I is e to the power of this one, x squared over 2. This gives you what? E to the power of x squared times q is what? We have x actually here. So this is x, here is x. This is true to me. And now, just the integration is easier. So integrating both sides, you'll obtain e raised x squared over 2 times y, which is half times e raised x squared. How? Just like this integration is easier. The integration of x e raised x squared dx. You can use the substitution. Yeah? Substitution, if you say u is equal to x squared, just like du by dx will be what? 2x. Then upon substituting here, it will be easy to find the solution. And of course, the solution is this way, this one. Therefore, y of x will be what? This thing is raised minus x squared over 2 times half of e raised x squared plus c. And upon using the initial condition, y at 0 is 1, because this will be 0, this will be 0, so this will be 1 plus c, yeah, half plus c, I mean, is equal to 1, therefore c is half. Half, that's true. Just like substitute it here in place of c, you can substitute it here. Then finally, you will obtain 1 over 2 e raised x squared over 2 plus e raised minus x squared over 2. And this is called the cos hyperbolic of x squared over 2. Remember, do you know the cos hyperbolic function of x is written as this one, e raised x plus e raised x minus x over 2. This is called the cos hyperbolic. And the sine hyperbolic of x is what? E raised x minus e raised minus x over 2. Now you can see that here, what's the difference? The difference is minus x squared over 2 instead of x. That's why it is cos hyperbolic x squared over 2. Therefore, the general solution is like simply cos hyperbolic x squared over 2 to 9. So this is all for today, and remember how to obtain the integrating factor, and everything will be easy for you. All the best.